Hello students, welcome to today's lesson where we're going to go ahead and be doing a review for the bonding test. And this is the test that you received the other day, and we're going to go ahead and review how to answer all of the questions on the test so that you can easily see it. Now, on the test, just like you're going to have in your actual exam, you want to make sure that you have your periodic table up. So we're going to go ahead and get P table right up here. And then we're going to go ahead and take a look at the test here. So the very first question, it's wanting us to go ahead and identify which one of these compounds is going to be ionic, okay? And the way that we can go ahead and test that in particular is that we're going to go ahead and just take a look to see which one of these has a combo that includes a metal and a non-metal, okay? And we're going to look for the one that has the most obvious example. So the very first one is T and V, or Ti and V, and we see that titanium's a metal, so we're off to a good start. But then we see that V is also a metal, so it's not going to be this one right here. And because of that, we can go ahead and kind of eliminate it from our options right there. So we're going to put that red because we know it's not it. Next, we're going to go ahead and look at G and Cl, Ge. Ge is right here, so it's a metalloid, which means that it is not necessarily a metal, or at least we're not treating it as one. And Cl is a non-metal. So here we have the non-metal, but it's paired with a metalloid. So at the moment, we're going to kind of put that kind of like a question mark. Okay. This one right here has zinc and oxygen. And we're going to go ahead and take a look, and we see that we have zinc and oxygen. Shoot, that means that we have a metal. This is a transition metal. Then we have their non-metal right here. That means this one here is going to be our answer, okay? And our answer, we're going to go ahead and circle that as red. We already know, or circle this one right here. We're going to make it a color we can easily see. We'll say that it's green. And then these ones here, we're going to go ahead and get them back to black right there, okay? And so now we know that C is our first answer, okay? Next, it's saying which type of bonding is the strongest. And this is just a case where you're supposed to memorize the different bond energies. All right. And the theory behind this particular one, okay, has to do specifically from the equation that we were working with, where we were working with Coulomb's law, where we had Q1 divided by Q2, and then all of this was divided by the radius squared. And when we think about Coulomb's law and we think about ionic compounds, what we know is that we know that ionic compounds always have full charges, okay? So that means that we'd have like a -1 charge and let's just say that we had a +1 charge, okay? Where we had these two charges together, this is going to go ahead and give us a full charge. And then this is going to be divided by the radius. If we had something that was covalent, that's where we have kind of like our point charges. So imagine if you had 0.015 and you were multiplying that by +0.016. That's all divided by r squared too. This would be like a covalent molecule where we only really have a partial charge instead of a full one, which means that that partial negative charge and that full one, when we multiply that together, that's not going to give us a lot of value for the energy in that bond, okay? And therefore, it's going to be a pretty weak bond. So that's why ionic bonds are going to end up being our strongest one. And it's because they have those full charges that are involved there. Okay, so our second answer ends up being ionic. Next one, 3. Which of the following should have the highest bond energy? Okay, and this is going to be a case where we're going to go ahead and look at two things. The first thing that we're going to look at is we're going to say, all right, we have single bonds and double bonds. Okay. So we're going to take a look at that and we're going to say, all right, so we know that double bonds have more energy than single bonds. All right. So automatically we know it's got to be between C and D because these are the two that have double bonds. Then we have to go ahead and see, well, shoot, which one is going to have the highest bond energy. And we can go back to what we were looking at before, okay, where we're going to have our two charges here, and then this is going to be defined by the radius as well, okay? And in general, the smaller the radius, the stronger the bond is going to be, okay? So that means essentially we have to go ahead and compare the radii between these two right here. And as we were going through and talking about the radius, what we notice is that the trend generally, as we go left to right on the periodic table, is that the elements end up getting smaller. Okay, so as an example here, carbon has 67 for its radius, whereas oxygen is only going to have 48. Therefore, the difference between carbon and oxygen and carbon, their sizes is going to be enough to help us figure out that, hey, this one should have the highest bond energy because it's going to have a smaller radius. And remember, our energy is divided by radius, so therefore we're going to have a smaller dividing factor or divisor. Therefore, we're going to have a higher amount of energy. So that's why this one here is going to be the answer, the C double bonded to O. All right, next we're going to go ahead and look at number 4. And it is saying, which of the following compounds has the smallest bond angle between the hydrogen molecules? Okay. And so this is a case where we're probably going to have to draw these out. Okay. So we're going to go ahead and we're going to copy them here. We're going to get a new one, create, and we have to draw them out. Okay. So we know that A is H2O, okay, and O, H2O, is going to be one of these molecules. Each H gives us 1 electron. Each O gives us 6, okay, which means that we're going to have a total of 8 electrons we got to draw. We've used 1, 2, 3, 4 in the bonds, which means that we have these lone pairs right here. And since we have 2 lone pairs, we know that this is going to push our hydrogens down with quite a lot of force, okay? And we're going to say, like, because of that, it's going to be less than 109, okay? Because 109 is kind of like our basic one. And I'll do C next so that we can see that. So C, this is an example where we have our 4 hydrogens. Okay, we draw this one out. We see we have our 4 hydrogens. This one has no lone pairs. And remember, when we have 4 things with no lone pairs, this bond angle is going to be 109. Okay, so this bond angle is 109 for C. H2O has much less than 109. Okay. Next, we're going to go ahead and do B so that we can go ahead and take a look. And B is going to go ahead and have N. It has 3 H's. Okay. N gives us 5 electrons. We have 3 H's, which means that we're going to have 3 from there, 3 plus 5. So we're going to have 8. We've used 1, 2, 3, 4, 5, 6, 7, 8. And we're going to go ahead and notice that we have 1 lone pair pushing on these, okay? So this is also going to be less than 109, okay? The only other question that we have, well, we'll go ahead and draw this one out too. This is a case where we're going to have F, H, okay, and H, okay? And this is a case where even though we have these extra electrons on fluorine, around this central atom, this one's still going to end up being 109. So that means that, first of all, we know that these two are less than 109. And we know that because our lone pairs are pushing on the hydrogens. Okay? So we automatically know it can't be either of these two. So we'll look at these two right here and we'll say, shoot, which one is going to push down those hydrogens more? And the answer is going to be this one right here, the H2O. And the reason that we know that is because instead of having one lone pair, we have two lone pairs pushing it down, which means that this one is going to have a much lower bond angle. And in fact, the bond angle for this one ends up being 104.5 degrees, whereas the bond angle for this one ends up being 107, okay? But by drawing it out and seeing that we had extra lone pairs, it lets us figure that out, okay? So we can go ahead and go here, and go ahead and highlight that. All right, next we have this one right here, and it's asking how many pi bonds and sigma bonds we have in the following compound. All right, so we're going to go ahead and first count our sigma bonds, and we're going to go ahead and know that sigma are the first bond that happens. Okay, so we're going to have 1, 2, 3, 4, 5, 6, 7, 8. So 8 sigma bonds, and we know this right away because we have 8 first bonds that happen. Next, we have to count how many pi bonds we have, okay? And pi bonds are going to be any double or triple bonds that we have. So here, between the nitrogens, we see we have 1 pi bond. And then between the carbons, we see that we have another pi bond in the double bond, which brings us to 2. And then we have a triple bond, which means that all together we have a total of 3 pi bonds and 8 sigma bonds. So we can safely say that our answer for this one is B. Number 6 is use Vesper theory to help us answer this question. And this is one of these questions that we're probably going to get something similar to it. That they like to ask these particular ones, and we're going to take a look at this nitrogen. And we're going to take a look specifically and say, hey, is there anything going on here that I don't see? And in particular, what we're going to notice is that this particular image does not have any lone pairs on it, okay? So I want you to go ahead and notice here that each nitrogen that we have here has 2 hydrogens on it, and then each nitrogen is connected to each other, okay? So if we were doing our full Lewis structure planning, we'd say, hey, each hydrogen is going to go ahead and give us 4 electrons. Each nitrogen would give us 5 electrons, okay? Or a total electrons from hydrogen is 4. For nitrogen, it's 2 times 5, okay? So that means that we have a total of 14 electrons that we have to draw. We've used 1, 2, 3, 4, 5 in bonds, so that means that we've used 10 total. Which means that we have 4 electrons that are left over. Which means that each of these should have these lone pairs here. So that means that here we have essentially a molecule that has these lone pairs, and we have these hydrogens right here. In that particular case, because we have both of those, we can confidently say that this bond angle is less than 109, okay? And since it's less than 109, we're going to have to put a number on it. And in this case, we're going to go ahead and just write that this number ends up being 107, okay? And we'll go ahead and put that right there. Okay. So we know that this is going to be 107 degrees because we know it's less than 109. And we have to draw our lone pairs to help us figure that out. Number 7. All right. This one right here, it's asking for which pair is the boiling point of the first compound higher than the boiling point of the second compound. So we're going to have to go ahead and compare what we know about boiling points, in particular, how this affects polar versus non-polar molecules. And when I explained this, I told you that there was a general rule for our molecules that we wanted to go ahead and say, hey, if we have nitrogen, let's refresh this one here. If we had nitrogen, chlorine, oxygen, or fluorine, that all of these were going to be polar molecules. And as we go across, they're going to go ahead and pull them just a little bit more. So if we have a compound with one of these, we're going to think, oh man, that's probably a polar molecule. So we took a look at A real quick. And we need to have the first one higher than the second one. So first of all, A has oxygen on the left as the first one, okay? And it has sulfur on the right in the same spot as the other one. So automatically we know, hey, A is automatically going to end up being our answer. Why? It has the oxygen versus the sulfur. Our sketch pad says, hey, if it has oxygen, it's likely going to be polar. This other one is likely going to be non-polar. Therefore, A will be our answer. Okay? And we could go through and see what would happen with all these other ones, just to double check. Here, in this particular case, we have an oxygen that's in the middle versus an oxygen that is all to the side, or two oxygens that are to one side. So in this case, since the oxygens are to the side, it's going to make that molecule kind of more polar because you have more electron density to one side, and that's going to make it so that it's harder for that to boil. Okay, so therefore this is one where the boiling point is higher on the right, because the one on the right has all the electrons on the side versus in the middle. C, you have an oxygen in the middle versus one that's in the side. Okay, so here, this one, it's going to end up being a very similar case where you have one on the side versus the middle, and that affects your boiling point. The last one is this pair right here. Here you have one oxygen on the right side versus two. The 2 is going to go ahead and make it even more polar, increase that pulling force that's available there. Okay. Therefore, A is our clear answer still. Question number 8. If element L and J are both able to form halides with the formula XCl3, the bond angle for element L is 90 degrees, and the bond angle for element J is 107. What is the identity of both J and L? Well, I think, first of all, I think I know that this is a incorrectly written question. I think that this angle, and I'll have to change it for next generations, is 120. Yeah, we're going to have to change that to... Oh no, 90 is correct. All right, we're going to keep that at 90. I see what's going on here. All right. All right, so this one right here, what we'll have to do is we'll have to go ahead and take a look and see, all right, which one of these is going to go ahead and give us a formula of XCl3, and then we're also going to go ahead and take a look to see which one is going to give us a bond of 90 degrees versus 107 degrees, okay? All right. So the very first thing that we're going to think of, and this is going to be pretty common that in a test like this, you'll go ahead and see element J is 107 degrees, and it'll let us automatically figure something out. So the very first thing that we should go ahead and recall, and since we're in this particular test, it should be easy for us to recall, is that, hey, whenever we had nitrogen and it had three things around it, it had this bond angle of 107 degrees, okay? Which means that if we had NCl, it's also going to have a bond of 107 degrees, okay? So that means automatically we can go ahead and say, all right, J is likely going to go ahead and be N, okay? Or it's also possible that it can be P, okay? Notice that both of these are in the same category, so that means that it could be either N or P, okay? Which means that right away, we have the luxury of being able to eliminate D altogether, okay? So D is eliminated altogether. We know that it cannot be that one, okay? Then we have to go ahead and look and say, all right, which one of these is going to go ahead and give us a bond angle of 90 degrees for element L, okay? Well, we know right away that it cannot be N, so it cannot be A because we determined that N also gives us a bond angle of 107 degrees, so it can't be A. B is having us look at iodine, okay? And iodine is going to go ahead and essentially still have the chlorines, but we're going to go ahead and have more of those electrons that are on there, okay? The very last one is aluminum and phosphorus, okay? Aluminum ends up being one of these post-transition metals. And metals, when they form bonds, they're going to form a lattice structure instead of a structure like that gives us angles, which means that we can automatically also eliminate C from our answers. All right? Therefore, B is going to end up being our answer where we have this one right here. All right, question number 9. Elements J and L are both in group 15. J and L each form gaseous covalent hydrides in which their oxidation number is -3. In the liquefied form of these hydrides, significant hydrogen bonding occurs only in the hydride of L. Okay, so which row about J and L could be correct? Okay, so what we see is that we see that they're going to make hydrides where their oxidation number is -3. Okay, which means that they're going to have 3 extra electrons, or it's going to feel like they have 3 extra electrons. So we're going to first check to see if we could figure it out directly off of that, and shoot, both nitrogen and arsenic can form 3. Okay, so that's not our secret to this question. In the liquefied form of these hydrates, significant hydrogen bonding only happens with the hydride of L. Okay, so now we have to think of hydrogen bonding. And hydrogen bonding is essentially just a polar bond. Well, polar bonds, that's only going to happen when we have N, Cl, O, and F, which means automatically L has to be N, which means that C and D are automatically eliminated from our answer choices. Okay? Then it's asking for our outer electron configuration. Okay? And this, really, we could just look at the periodic table for this. Okay? We see that, hey, this is our outer shell. It has 1, 2 in this block right here, which we know is our S block. Then it has 1, 2, 3 in the P block, which means that we can go ahead and safely say that, hey, the answer for this one should be B, because L has to be nitrogen, and it has 2 S's and 3 P's. Okay. Next, number 10, it's going to go ahead and say what is the shape that we would go ahead and expect for the following molecules. And in this case, it has NH3 and ALH3. Okay. NH3 is going to be a case, we've been drawing this one all day. It has 3 H's around it, and it has that dot. And this one's going to end up being pyramidal, trigonal pyramidal. Okay. So therefore, we have these two. ALH3, this is a case where we have aluminum, and it looks like it's one of those weird cases where aluminum is sharing its electrons instead of giving them up. And that's going to happen every so often with some of our metals that are in this bubble, and aluminum is one of those special ones that kind of does that. And that just has to do with its electronegativity. Okay. Its electronegativity is 1.61. Hydrogen's is 2.20. It's going to share it because the electronegativity of hydrogen isn't quite enough to take it all the way. Therefore, we're going to have to draw what that would end up being. Okay. So when you draw it out, what you would notice is that aluminum has a total of 3 electrons that it's going to go ahead and give up. Okay, each hydrogen, and there's 3 of them, gives us 1, so we're going to have a total of 6 electrons. So we'd have Al with 6 hydrogens around it, okay? And in this case, we see that we have used up all 6 of our electrons, 1, 2, 3, 4, 5, 6. Because we've used up all 6 of our electrons, we know that this is what it is, and we take a look and say, all right, we have 6 electrons, no lone pairs. We know that they're going to spread out in a circle as far as they can. That's going to be 120 degrees. That's going to be trigonal planar because they're all spreading out and they're all in the same plane. Therefore, A is going to be our answer right away. Okay. I'm going to go ahead and check my timing, and it looks like we have been recording for quite a while, so I'm going to go ahead and pause the time and work on the free response section a little bit later. But hopefully this helps us to figure out the answers that are in this first section right here.